So yesterday we found the inverse of linear functions, which were, what type of functions were the inverse? Linear function had a linear inverse, okay? We also looked at quadratic functions. What were their inverses? What's the inverse of a square? Well, it did. We restricted the domain, but what did we call it? We took the
inverse. Y of x.
What's the opposite of a quadratic? It's the opposite of squaring something. Square root. Okay, the inverse of quadratic was the square root function. What we're going to look at with example 3 here, we're going to look at a couple of exponential functions, then we're going to look at a couple of logarithmic functions. So the process still remains the same. We switch x and y to begin with. So we've got x is equal to 4 to the y. Now reach way back to a couple of weeks ago when we started exponential functions. If we're solving for y and y is stuck in the exponent, how do we get it out of the exponent? Put it in log form, okay? Log, the base of the exponential is the same as the base of the logarithm, so it's log base 4, and the other two parts switch places, okay? So here's the way to look at it. It was 4 to the y. So the y needs to be nowhere close to the 4. The y needs to go to the other side of the equation. The x is now inside the logarithm. And that's all we have to do. It is in log 4, or it is solve for y. So f inverse of x is log base 4 of x. Exponential functions and logarithms are inverses. The inverse of an exponential is a logarithm. Inverses are what undo them, okay? So a square root undoes squaring. Logarithms undo exponentials. Okay, let's look at B. When we switch x and y, we get x equals e to the y. Again, to get the y out of the exponent, we write it in logarithmic form. We kind of breezed over this part, but if the base is e, we use the ln instead of the log. Only when the base is e. We use the ln instead of the log, and we don't have to put the base. Okay? Just like if you see the log without a base, it's understood to be what? 10. Okay? If you see the ln, the base is always e. All right? So g inverse of x here is the ln of x, the natural log of x. You're probably wondering if it's the natural log, why is it not NL? Okay, it's because it comes from, I think it's Latin is where this originated. So in Latin, it's spelled, it starts with an L and there's an N in there somewhere, okay? All right, let's look at C and D. Okay, let's look at C and D. We've got h of x is equal to log base 5 of x. So we switch x and y. Let me switch colors since I switched functions. Okay. X is equal to log base 5 of y. Okay. If the variable that we're solving for is in the logarithm, what do you think we're going to do? Put it in exponential form. So remember, exponential form, we use the swoop. We start with the base. We go around the equal sign, and we end up back in the logarithm. So 5 raised to the x is equal to y. So h inverse of x is equal to 5 to the x. Okay, last one here. K of x is equal to the natural log of 3x. Switch x and y, the natural log of 3y. I always do my ln in cursive because my l's and 1's look the same. So anyways, that's why it's like that. Okay, if we put this in exponential form, it's understood to have a base of e. So that's e to the x equals 3y. Y is not by itself. How do we get it by itself? Divide by 3. So we have k inverse of x is equal to e to the x, that whole expression divided by 3. Okay, questions? Let's look at example 4. Okay, sometimes they will ask us questions about the inverse and they don't give us a function rule. Okay, they don't give us a quadratic, or they don't give us an exponential or a logarithm or a linear function. They don't give us the rules, so we can't switch at x and y to find the inverse. Sometimes they might just give us a table. So let's look at what they've given us here in example A. It says, suppose that assignments for the function f of x are as shown in the following table. Make a similar table that shows the assignments made by f inverse of x. Then describe the domain and range of the function and the inverse. Okay, so sometimes tables can be a little overwhelming. So let's just kind of take this back for a second. I'm going to write this first entry here. -4 is x, f of x is 2. I'm going to write that as a point. Okay, I'm going to write that as a point. So that is the point, -4, +2, for the original function. Well, back when I was explaining inverses, what did I tell you that the inverse does? What does it switch? It switches the y and the x. So if -4, +2 is the point for the original function, then +2, -4 is going to be the point on the inverse function. Okay, so I'm going to come over here to where x is +2, then the y value is -4. So I'm going to put that in that box right there. Okay, so let's do the same thing here. -3, +1. So that would give me the point +1, -3. Now, it's looking like these values are already there. We're going to talk about that here in a second. Okay, but let's keep going. On the original, we've got -2, 0. So on the inverse, that's going to be 0, -2. On the original, we have -1, -1. So on the inverse, when we flip those, it's still the same thing, -1, -1. The original is the point 0, -2. So the inverse is going to be -2, 0. The original has 1, -3. So the inverse is going to be -3, +1. 2, -4. So the inverse is -4, +2. We've got 3, -5. I don't have -5 on my table, so I'm going to add it. -5, +3. 4, -6. So that's going to be -6, +4. So guess what? Technically, I can go back with these points. -5, +3 on the inverse would be +3, -5 on the original. Okay. So this is kind of weird. We ended up with the exact same y values for the inverse as we had for the original. Some functions are their own inverse. Some functions are their own inverse. So how could we test this? If we look at this table of values, just look at the x and the f of x part for a second. Could we write a function rule? Could we come up with an equation for f of x? What type of function does it look like it is? What's happening to our y values? What's happening to our y values for f of x? We're subtracting 1 every time. What type of function is that?
Linear.
Linear. If your y's change by the same value every time, that's a linear function. So what would be the equation for that linear function? -x, because we're subtracting 1, right? And what's the y-intercept? -2, because when x is 0, the y value is -2. -x -2 is the rule for f of x. Now that we have a rule for it, let's find the inverse. Okay, let's go through the process of finding the inverse to see if this is true. If we find the inverse, do we get the exact same function? Okay, so switch x and y. Okay, solve for y. Add 2 to both sides, so x plus 2 is equal to negative y. Divide the whole thing by negative 1. That changes our signs. Looky there, we got the exact same equation for the inverse as the original function. It doesn't happen very often, okay? But some functions are their own inverse. Let's go back and let's confirm this with the graph too. Okay, let's confirm this with the graph. Let's graph negative x minus 2. What did I show you was true when we look at the graphs yesterday? What's true about an inverse function when we look at the graph? What other line did I graph? That line y equals x. Okay, that line y equals x. I'm going to square up my window. Okay, there's my function. There's the line y equals x. What were we looking for with that line? Was it symmetric? Tilt your head or tilt your calculator. Does the left side of this function fall on the right side of the function? It does. Okay, it does. It may be, kind of hard to see. It might be a little bit of a question, but it looks pretty close. If you tilt your head so that y equals x is completely vertical, if we flip that left side over, it's going to fall right on that right side. So this function is its own inverse. We've just proven it 3 ways. When we built the table of values, our y values were the same thing. So then we wrote a rule, and we found the inverse using the rule. We got the exact same function. So we graphed it, and we saw that symmetry across the line y equals x. So 3 different things that you need to be able to recognize about inverse functions. Okay. All right. So speaking of looking at the graph, what if they just give us random points? Okay. What if they just give us random points and want us to graph the inverse? We're going to do the same thing we did in that table, guys. We're going to take the point. We're going to switch the x and the y coordinates. That's going to give us the point on the inverse. So if we have -5, -3 on the original, on the inverse, that's going to be -3, -5. I already graphed the line y equals x on there, so you can see that it reflects over that line. Okay, so if -2, -1 is on the original, what's going to be on the inverse? -1, -2. If -4, 0 is on the original, 0, -4 is on the inverse. -3, +1 is on the original. +1, -3 is on the inverse. -1, 2 becomes 2, -1. 0, 4 becomes 4, 0. 2, 3 becomes 3, 2. And 1, 5 becomes 5, 1. So you should be able to see, if you tilt your paper there, you should see mirror images. All these points should be mirror images across that line y equals x. So all these red points here are the points for the inverse of g. Okay. So the last slide there that I've got on your paper is supposed to be a check your understanding for you. Okay. So the first one says, which of the graphs below show functions that have inverses justify your response? So we talked about that yesterday. Compare graph 1 and graph 2. One of them, the inverse is a function. The other one, the inverse is not a function. And then I want you to find rules for the inverses for those 2 functions right there.